Kia ora and welcome to question 2 of the 2008 SCOL Calc exam. This question here is all about complex numbers. The part A and B questions are pretty standard. Part B flows on from that, and then part C has got a bit of geometry involved. And we're plotting solutions on the Argon diagram with a complex plane. Okay, so for the first question, there's actually many different ways you can solve this problem. Okay, they're asking us to solve the equation z plus 1 cubed equals 8. So z plus 1 cubed equals 8 has 3 solutions to it because it's a cubic. The way that I look at it is I just think about this thing here and what it needs to equal. So if I said like u cubed equals 8, where u is equal to z plus 1, u cubed equals 8 has 3 solutions to it. One of them is obvious, u is equal to 2. We'll call that the first solution. And then the other 2 solutions, u2 and u3, great band u2, 2 cis 2 pi over 3 and 2 cis negative 2 pi over 3. Okay, and the reason I can solve those really quickly is because I know that there's some symmetry around the origin. So if u cubed equals 8 is the problem I'm trying to solve, then the first solution is 2, because 2 cubed is 8, and the other ones are there and there. Those are 2 away from the origin. The solutions are spaced equally, therefore the angle or the argument for the second one is 2 pi over 3 around, and the argument for the third one down there is 2 pi over 3 clockwise, or another 2 pi over 3 anti-clockwise. Okay, so they're the solutions to the problem for u cubed equals 8, but I need to solve the original question, z plus 1 all cubed equals 8. Well, that's pretty simple. I just need to subtract 1 off all of the u values to get back to the z values. So z1 is going to be 2 minus 1. Cool, 1. Well, that's the obvious solution of that problem, right? 1 plus 1 is 2, 2 cubed is 8. The second solution, I need to take 2 cis 2 pi over 3 and subtract 1 from it. Now that's a polar form expression minus 1. I need to then turn it from polar form into rectangular form if I want to subtract 1 from it. So let's look at that in the Argon diagram. That solution is this one, and use a little bit of trig. Drop that right angle triangle down there. It's got a hypotenuse of 2, and the angle in here is pi over 3. 2 pi over 3 is 120 degrees, and pi over 3 is equal to 60 degrees. So that's a special angle. 60 degrees with a hypotenuse of 2 tells us that that's root 3, and that's 1. So 2 cis 2 pi over 3 is the same as minus 1 plus root 3 I. Because 1 in the adjacent side of that triangle is on the left-hand side of the origin, so it's a negative real part, bearing in mind that's the real axis and that's the imaginary axis. So negative 1 plus root 3 times I, and then minus 1 from that is minus 2 plus root 3i. And then lastly, z3, we take our third solution for u, 2 cis minus 2 pi over 3, take away 1 from that. Okay, now that solution, I haven't really done a convincing job of it, so let's just tidy up this diagram a bit. u3 has exactly the same real part. It's just got a negative imaginary part. Now we're expecting that because we have an equation that has no imaginary stuff in it, right? This equation here, real coefficients. And when an equation, a polynomial equation, has real coefficients, the solutions must come in conjugate pairs if they've got imaginary parts. Okay, so our solutions that are the complex solutions, z equals 1 is a purely real one. The other 2 must be conjugate pairs. So minus 1 minus root 3i, and then take away 1 from the u value to get the z value, minus 2 minus root 3i. There are 3 solutions to the problem. Let's go back to this question, z plus 1 all cubed equals 8. This question here, like I said, could be solved in different ways. It's an easy one in the sense that the power is only 3, so you could just cube the binomial on the left-hand side, move the 8 to the other side. I'll leave you to check that the cubing thing worked. If you want to write 3 brackets out, you can, but the binomial expansion formula definitely is helpful. And then we could just bang that into a graphics calculator and check that the 3 solutions to that are the 3 solutions we've just found. You know that there's a real solution to this problem. You know that z equals 1 is the obvious one. You can spot that by just staring at the problem long enough. So z equals 1 is going to tell us what one of the factors of this cubic is. So if you didn't have a graphics calculator, you would need to then go, okay, z equals 1 is a solution, so z minus 1 is a factor. And then you go through factorizing this cubic equation. This is all extra stuff because we've already found the answers using de Moivre's theorem. Minus 1z squared means that this is going to be 4z, and then minus 4z would mean that this is going to be plus 7, and then we solve this using the quadratic formula, or completing the square. Z plus 2 all squared, plus 3 equals 0, z equals minus 2 plus or minus root 3i. So look, we've got the 3 solutions there using probably a quicker method in this case, but you just need to think about what would happen if you increase the power from a 3 to say a 5. Then expanding it out and solving a power of 5 equation is going to be a lot harder than using the symmetry of the roots and then just taking 1 off all of the roots once they're in rectangular form. Okay. I've just gone off on a bit of a tangent, so let's just go back to the question, make sure I've answered it. Solve the equation, done. Give your answers in terms of w, where w is a complex number and w cubed equals 1. Okay, we haven't done that part. I don't know why it's necessary, but let's do it anyways. Hence or otherwise show that the sum of the roots to the problem is negative 3. Well, we can find that third part without doing that second step. But it does tell us we have to do the second step. The or otherwise just says if we didn't do the second step, we can solve the third step in any way that we please. So let's just do the third step first. Sum of the roots is minus 3. Okay, where does that come in? We've got our 3 roots. 1 minus 2 plus root 3i minus 2 minus root 3i. Sum of the roots is equal to 1 minus 2 equals minus 3. Done. Or you look at the cubic equation that we got, and that term there is always minus the sum of the roots. Okay, if you weren't aware of that, if you've got a cubic equation that's written in this format, in our case a is 1, but in general the sum of the roots of the cubic will always be minus b over a. So in our case it's minus 3. That's a different way of solving the problem. But what does this w cubed business mean? Give your answers in terms of w, where w is a complex number and w cubed equals 1. Okay, w cubed equals 1's got 3 solutions. W equals 1, let's call it w1. w2 equals cis 2 pi over 3. And w3 is equal to cis minus 2 pi over 3. Very, very similar to the problem I solved, which was u cubed equals 8. So if we go back to the work we've already done with the u cubed equals 8 business, that bit there is one of the w values. That bit there is another w value. And we're assuming that w is not just 1, because it says w is a complex number. If we make w just equal to 1, then we won't get the other roots in terms of w. So let's just pick, this one. Let's make that w. It turns out it doesn't matter, but as long as it's not the 1. If we pick that as our w value, then our solutions to the problem, if we go all the way down here, well, one of them is just going to equal 1. The second one is equal to 2w minus 1, because remember that this was w. And the other solution to the problem is not 2w minus 1, because as soon as I make cis 2 pi over 3 w, I can't then go and say that that one's also w, because it's the conjugate of w. But using the symmetry, cis 2 pi over 3, where does that sit? Remember, w, that's the first w. Second w is up here, 2 pi over 3, which I'm calling w, cis 2 pi over 3. And then if I square that, I'd get cis 2 pi over 3 all squared, which is equal to cis 4 pi over 3. Okay, or cis 2 pi over 3 multiplied by the same thing. I add the arguments and I get 4 pi over 3 as the argument. And that turns out to be just another 2 pi over 3 around, which is the third solution. W3 is actually just w squared. If you're interested in why this occurs, look up the roots of unity, because it's a common thing, sort of common thing that turns up in complex numbers problems. And so what that means is that the third solution, z cubed, so not z cubed, my bad, z3, can be written as 2w squared minus 1. Okay, part B is to solve an equation. It's very, very similar, but a bit different. And so what we should do is try and exploit the similarity between the first question and this one to save us having to do a whole heap of double up work. However, just like the last one, this is a cubic equation, which means that expanding it is not that nasty, and expanding and solving a polynomial possibly is an easier thing to do. So we're going to look at both methods again, but you just take your pick. The first one, z plus 1 cubed equals 8. So we go recall z plus 1 all cubed equals 8. Had solutions of z is equal to 1, z is equal to negative 2 plus root 3i, and z is equal to minus 2 minus root 3i. Now we're, in this question, asked to solve a slightly different problem. Z plus 1 cubed equals 8 times z minus 1 cubed. So what I'm going to do is take this part down the bottom left and sandwich the cubic terms together. So z plus 1 all over z minus 1 all cubed is equal to 8. And then I've got another situation where it's something cubed equals 8. So I'm going to say solve u cubed equals 8, where u is equal to z plus 1 over z minus 1. Now I've already solved u cubed equals 8. The solutions to that were u1 equals 2, u2 is equal to 2 cis 2 pi over 3, and u3 was 2 cis minus 2 pi over 3. But I'd already converted them as well. I'd converted them into a rectangular form. That was minus 1 plus root 3i, and that was minus 1 minus root 3i. So I've got these three solutions. I then need to dump these three solutions here, all into there individually, solve a linear equation for z. Okay, so to do that, let's do the first one. u1, so 2 z plus 1 over z minus 1, 2z minus 1 is equal to z plus 1, 2z on the left, take away the z on the right, you get z minus 2 on the left, add it to the right, you've got z is equal to 3. Okay, so that's That's the real solution to this problem. A nice real solution, which means if we solved the cubic by expansion, we'd get a nice solution. That's quite helpful. Okay, and then the other ones, U2, got -1 plus root 3i equals to z plus 1 over z minus 1. This one here is not as nice to rearrange. Okay, leave the terms with the z on the left hand side. So we've got -1 plus root 3i all times z. And then we've also got a z on the right that moves to the left, so -1 all times z. And on the right hand side we've got a 1. We also need to move that complex number on the left, which is -1 plus root 3i times -1. Move it to the other side as plus -1 plus root 3i. Okay, and then divide. Z is equal to root 3i all divided by -2 plus root 3i. This stuff is all tedious achieved level stuff, so you could use your graphics calculator at this point, but as I'm recording this video, I don't have the calculator next to me. So let's just do it manually. Why quit when we've gone so far? -2 minus root 3i over -2 minus root 3i. Denominator becomes 4 plus 3 is 7. Numerator becomes root 3, because root 3i times negative root 3i is -3 times, oopsies, not root 3, -3 times I squared, so 3. And then we've got minus, because this is here's in brackets, root 3i times -2 is -2 root 3i. And then we don't, fortunately, we don't have to do the same thing for U3. But if we did, we would just be replacing this dude with the conjugate, -1 minus root 3i, and then going through the same processes. But the equation we're solving, again, it has real coefficients to it. This equation here doesn't have any imaginary stuff in it. Solutions have got imaginary terms, but the coefficients don't. Therefore, any complex numbered solutions must come in conjugate pairs. So the solution we found there, 3 over 7 minus 2 root 3 over 7i, U3 will be equal to 3 plus 2 root 3i all over 7. Okay, now let's check that we've got the right solutions by doing the expansion method. Let's go back all the way to this problem here and just expand the left-hand side. Z cubed plus 3z squared plus 3z plus 1. And the right-hand side has an 8, but then it's z minus 1 all cubed. So that will be z cubed. Z times -1 occurs 3 ways, so that's minus 3z squared. Z times -1 times -1 occurs 3 ways, that's a 1z times 3, 3z. And then -1 times -1 times -1 only occurs once. Only one way of doing it, that's -1. Rearrange this by moving everything to one side. Oopsies, not 7 cubed, 7z cubed. Minus 24z squared on the right, minus another 3 makes minus 27z squared. 24z on the right, minus another 3z gives you 21 z. And minus 8 on the right, take away another 1 makes minus 9. Chuck that into the graphics calculator to solve using the polynomial solver, or try and find a real solution to this problem. And it turns out, as we found earlier, the real solution to the problem is z is equal to 3. So in the answers it says by inspection. If they want you to solve a cubic manually, there'd have to be a nice answer to the problem or a hint. Actually, they gave us a whole heap of hints, we've used it, but if this was an isolated problem, we would need to know that z minus 3 is a factor. Then we complete the factorization. I'll leave you to check that, and solving the quadratic equation using the quadratic formula. Z is equal to 3, or Z is equal to minus B plus or minus B squared minus 4AC all over 2A. The thing underneath the square root there is 36 minus 28 times 3. It comes to be root negative 48. Um, 6 over 14 is 3 over 7, which was what we had earlier. The root 48 thing, we can write that as 16 times 3. Pull the 16 out of the square as a 4. 4 over 14 is 2 over 7. So we get 2 over 7 root 3i, which I believe is what we had. Yes, it was. So there are the three solutions. Again, let's just go back to the question. Have we solved that and answered the question? Yes, giving exact answers in rectangular form. So the method that we used rectangular form. It solved the problem, solved this problem here using polar form. I did the conversions into rectangular form using trig, and then I solved algebraic equations to find the z values in rectangular form. Okay, last question. Plot the three solutions to the equation in the complex plane as the points A, B, and C. Plot the three solutions to this new equation in the complex plane as the points E, F, and G. Another cubic equation. This is a very repetitive question, hence why we need to use the symmetry. How does this problem compare to the previous? The z has been replaced with a 1 over z. In other words, the solutions to part B, if we take the reciprocals of them, we get the solutions to part C. Okay, so let's do the first part, which is plot the solutions we've just found as points A, B, and C. So z is equal to 3 was one of them. Let's call that A. We had 3 over 7 plus 2 root 3 over 7 times I. Probably use a calculator to get this roughly to scale. So 3/7 is the real part, and it's 0.428. So about there. And then the imaginary part, 2 root 3 over 7. If we work that one out, we get 0.494. So 2 square root 3 over 7i. About half, about there, and the other one is just down below. That's a triangle. Okay, and then we want the other equation. We plot those three solutions in the complex plane as the points E, F, and G. Show that the ratio of the areas is 81 over 49. Okay, so we could either use geometry or we could use algebra to solve this next part of the question. But we're now wanting to solve, we'll take these three solutions for z. So z is equal to 3, so 1 over z is equal to 1/3. Or z is equal to 3 minus 2 root 3i all over 7. And we want the reciprocal, 7 over 3 minus 2 root 3i. Now that there is not in a standard form, so we need to do the conjugate stuff again. Okay, we could just get a calculator to evaluate this stuff. There's not really scholarship level thinking in working it through. It turns out, if you look at the schedule for this year, if you use the whole W stuff from earlier, things tidy up a little bit. But this, yeah, like I was saying, this is just an achieved question. We just evaluate, work out what it is. So the denominator there, 3 squared, 9. 2 root 3 times 2 root 3 is 12. So the denominator becomes 9 plus 12. and then the numerator 21, 7 times 3, and then 7 times 2 root 3i, 14 root 3i, which is 1 plus 14 over 21 simplifies to 2/3, so 2/3 root 3i. Okay, and then because, again, this problem only had real coefficients, the third solution, when we take z is equal to 3 plus 2 root 3i over 7, if I was to reciprocate that, 1 over z is just going to become 1 minus 2/3 root 3i. So we need to plot these on the diagram as the points D, E, and F. Hence why I was doing things to scale. Let's use a different colour for the 1 over z ones. Remember that B and C had a real part of about 0.5, so D is in here at 1/3. B had a real part and an imaginary part of about 0.5, so E is going to be double that height, and 2 over 3 times root 3 comes out to be 1.15. So we want a real part of 1 and we want an imaginary part that's 1.15. So somewhere, I guess about there. And then 1 directly below that. Something like that. Alright, so that's another triangle. Close enough. And we want to find the ratio of the areas of that triangle. Now, like I was saying, there's another way of getting that problem. We just took the reciprocals of the three solutions, used conjugates to rationalize the denominator, and then it wasn't too bad. But another way of thinking about it was if we were taking a solution to a problem and then we're taking the reciprocal, it's the same as powering it by -1. So if you had some solution, z is equal to r cis theta, and you want to take that to the power of -1, it's just r to the -1 cis negative theta. And so looking at the diagram there, the complex number b, for example, had an angle of, say, theta. Running out of colours. So b here has some angle theta. When we reciprocate it, all we do is flip it upside down to have a solution of minus theta. Not a solution, sorry, an argument of minus theta. And then the modulus of b, which is actually a number less than 1 for that problem, when we take the reciprocal of it, the modulus is 1 over the original modulus, which means it's kind of scaled up to this point f. For example, if the modulus of b was 1/3, then the modulus of f is going to be 3. Okay, then lastly, if we want to find the ratio of these areas, so triangle ABC, I'm just going to use the fact that I know these complex numbers in rectangular form. So if I want like half base times height, I can look at this triangle ABC here, and say like the base is the distance between B and C, which is 2 times the imaginary part of B, or the imaginary part of C, so that was 3 over 7. So no, it wasn't. It was 2 over 7 times root 3. So that length BC is going to be double that, for root 3 over 7. There's a half as well, area of a triangle, half times base 4 root 3 over 7. Don't worry about the I, because that's just the direction. It's like a unit. And then the base of that triangle has been found. We need the height of it, which is the distance between the real part of B and C and the real part of A. So remember that this dude in here is 3/7. So to get to the point 3, we need to add another 4/7 to get to 1, and then another 2. So it's 2 and 4/7, so 18/7. Okay, that's the area of triangle ABC. Now divide it by the triangle DEF, do the same thing. A half times the base. The base is the distance between E and F. Okay, E and F, the imaginary part, 2√3/3 for both of them, so we double that. We get 4/3 times √3. And then the distance between D and the real part of E and F. The real part of E and F was 1, and D was a third. So we're going from 1/3 to 1 to 2/3. Alrighty, working all this out, stuff cancels, the halves cancel, the √3s cancel, the 4s cancel, and we're left with 18/49 on the top, divided by 2/9 on the bottom, 18/49 multiplied by 9/2. 18/2 is 9, so we've got 81/49.